Okay, so now let's resume with Willy Cortiñas, who's going to speak on the classification of Leavitt path algebras. Right.
Okay, so thanks very much for the invitation. And okay, so I'm going to revisit one of the questions that Ruthbe asked in his lecture today. So I will talk about SPI graphs. Today, all my graphs will be finite. Okay, this is a hypothesis I will assume without repeating it. Okay, so we say that E is SPI if it satisfies a number of properties. So first of all, it has at least one cycle. So what is a cycle? A cycle is a closed path in the graph. And well, so a closed path could, you know, you can go ahead and then go here and come back and then go here and so on. So a cycle is a closed path that doesn't go over any vertex more than once. Okay, so it's the simplest closed path. So one condition is that it must have one cycle at least. Second condition is that every cycle has an exit. And what is that? What is an exit? So an exit from a cycle is an edge that departs from a vertex in the cycle, but so that the edge is not itself part of the cycle. So for example, this is an exit, but this is also an exit. Because even if it brings you back to the cycle, the edge itself is not part of the cycle. Right? So this is a cycle, and this is another cycle, but this one is not in this cycle. And at the same time, this one is an exit for the bigger cycle. Okay? So that's the second condition. And the third condition is that every vertex is connected to every cycle. So, I mean, it's something that bothers me in this subject is that people say vertex are connected, so every vertex is connected to every cycle, and obviously connected, I mean, right? So this is connected to this if what? Well, if there is some path, but in which direction? I mean, does it have to be directed? It doesn't. Well, it means a directed path from the vertex to wherever you are going. So for every vertex here, there should be a path that lands, I mean, not just an edge, but a path that lands somewhere in the cycle. And if it has more than one cycle, then you should have the same with every cycle. So observe that if E is SPI, then it cannot have any sinks. So E is regular. So regular for a finite graph means that it has no sinks. Okay. So now, so these are the kind of graphs I'm interested in. And then I will have a Leavitt path algebra, and to have a Leavitt path algebra, I need to specify a ground ring, which can be a field, but then I also want it that they be allowed to be the integers, for example. So, sorry about that. My ground field is not called K, but L. Hope it doesn't come as too big of a shock. So L is the ground ring, which means it is commutative and unital. And L of E is the Leavitt path algebra of E over L. Okay, since little l is fixed, I do not write it every time. So a remark is that if L is a field, then E is SPI if and only if the ring LE, which has an implicit subscript L, is SPI. And what does it mean to be SPI for a ring? So R SPI means that for every non-zero element, there exists A and B, so that AXB is 1. So this is a strong condition of simplicity. Yeah, sorry. Yeah. Yeah, division rings satisfy this, but I'm asking that it not be a division ring. And that satisfies this. So this is a strong version of simplicity because a ring is called simple if every ideal, every two-sided ideal is either 0 or the whole thing. And this translates into saying that, so simple means that under the same circumstances there exists A1 AN and B1 BN, so that the sum is 1. Because this is this is a typical element of the two-sided ideal generated by X is such a sum. Right? You want 1 to be in the ideal generated by X. Right? And pure infinite simplicity asks for this to be true with one shot, with just one summand. Okay. And so as a recap, then E is purely infinite simple or simple purely infinite if and only if the Leavitt path algebra is purely infinite simple, at least when the ground field, the ground ring is a field. If the ground ring is not a field, then it will have ideals, since my L is commutative. And if it has ideals, then this ideal generates an ideal in LE, so LE will not be simple, much less purely infinite simple. Okay. Sorry? Yeah, it's also true for the sister algebra. Yeah. Okay. So, okay. So, for a regular, by the way, if you assume from the beginning that it has no sinks and no sources, then these conditions are equivalent to the condition that Ruthve mentioned this morning, that E be highly connected. Okay. So, okay. Thank you. Yeah, this is better because there was a shadow over that. Yeah. Okay, so we have E irregular graph, such as my SPI graphs, and then AE is the incidence matrix. This is a matrix indexed by the vertices. So that the VW entry is the number of edges that depart from B and land in W. Okay? And then there's the Bauer-Franks group is the cokernel of I minus A E T. And this has a distinguished element, as pointed out by Ruth today, which is the sum of the classes of the vertices. Okay. So there is a canonical map from the Bauer-Franks group to K0 of LE, and can E is an isomorphism if L is a field or a PID. And in general, there's also, I mean, since LE is an algebra over little l, there is also a homomorphism K0 of L to K0 of LE. And the two together induce a homomorphism here. And the kind of rings I'm interested in, which are more general than just fields or PIDs, all satisfy that this one is an isomorphism. Okay, so if, for example, L is regular Noetherian, then this is an isomorphism. Okay, so I will go back to that later. So we have a canonical map here too. Okay, so the open problem that was mentioned by Ruth today is that if L is a field, and E and F are SPI, and we have an isomorphism that tends 1 to 1, then, so the question is whether this implication holds, then there is an isomorphism of the Leavitt path algebras. Notice that an isomorphism of unital rings necessarily maps the unit to the unit, right? And if it maps the unit to the unit, then, and by the way, this one in this homomorphism maps the unit to the class of the unit, which Ruth will write the class of LE because he thinks of K0 as coming from projective modules. I think of it as coming from idempotent matrices, which is equivalent. And so I think of 1 as the 1 by 1 idempotent matrix that has a 1, right? Okay, so since 1 goes to 1, if these are isomorphic, then the induced isomorphic, I mean, applying K0 to this isomorphism gives an isomorphism that maps 1 to 1. So if this is true, then we must have this. The converse is true. Okay, and what is known is the following. So say you take L E over the complex numbers, right? Then this carries an involution, which, I mean, for this you do not need the complex numbers. It is equipped with an involution that maps vertices to themselves. And what does this mean? But this identity, you cannot discuss it, right? But what this means is that the involution applied to E is the ghost edge associated to E. And it's an involution. So if we apply it twice, so what is the involution applied to the ghost edge? Well, the edge. because when you apply it twice, you're gonna get that. And where does the C play a role? Well, if you have some lambda in C, then lambda star is the complex conjugation. So because this is a star algebra, it has associated a norm. In principle, it would be a semi-norm, but in this particular case of the Leavitt algebra, it is a norm. And then you can complete with respect to the norm. Completed with respect to this norm, and this is what is called the C-star algebra of E. Okay, then it is known that E is SPI if and only if C-star E is SPI, where SPI means in this ring theoretic sense, and by a theorem of Rotterdam using results of Kunz, the hypothesis BFE isomorphic to BFF with 1 going to 1 does imply that C star E and C star F are star isomorphic. So there is an isomorphism which on top of being isomorphism also preserves the involution. Right? So the involution induces an involution after completion, and this is preserved. So of course, if you have an involution, an isomorphism here, and this would preserve the involution, then it would pass to the completion, and we need to use an isomorphism here. And also, if you have the isomorphism here, then you can, LE sits inside here, then you can compose, and you get a homomorphism from here to here. But there is no reason why it should land here. So that's the whole point. Okay, so this is the motivation why one might ask whether this is true or not, because it's true after completion. And so what I want to talk about is a result that says that, well, I don't know if Leavitt path algebras with isomorphic Power-Franz group are isomorphic, but what I do know is that they are homotopy equivalent. So I need to tell you about homotopy. Okay. So say you have two algebra homomorphisms, then an elementary homotopy H from phi to psi is an algebra homomorphism H from A. Let me write it here. Here is A, here is H. We go to B of T. Here we have with phi and psi together, we can form a homomorphism to the Cartesian product for direct sum, right? Direct sum as abelian groups, right? The Cartesian product. And we ask that the diagram commutes when here I put evaluation at 0 and evaluation at 1, right? So this sends P of T to P of 0, P of 1. Notice that P of 1, if P is a polynomial sum of AI Ti, then P of 1 is sum of AI, right? So you don't need B to have a 1 so that you evaluate P at 1. It's the sum of the coefficients, which you can do even if the ring doesn't have a 1. Okay, so this is what an elementary homotopy is. Now, being elementarily homotopic is symmetric and reflexive relation, but it is not transitive. So, to define homotopy between homomorphisms, we have to allow for a finite sequence of elementary homotopies. Right? So we say that phi and psi are homotopic if there exists a sequence phi 0, phi 1, etc., phi n equal to psi, and homotopies h1, h2, up to hn. These are elementary homotopies. Okay? And, well, we say that phi from A to B is a homotopy equivalence if there exists psi from B to A, so that psi composed with phi is homotopy equivalent to the identity of A, and phi composed with psi is homotopy equivalent to the identity of B. Okay. Right. Okay, so this is, so my conclusion will be that under these circumstances, there are homotopy equivalencies from LE and LF and backwards. And I need some hypothesis on L, which will include both the case when L is a field and the case when L is a PID, and the case when L is a regular Noetherian ring, and much more. So, say R is a ring. Okay, so we say that R is regular if for every R module M there exists a finite projective resolution where N depends on M. So, for example, if R is a field, then this holds with N equal to 0 for all M. If R is a PID, then it holds for N equal 1 for all M. And if R is regular Noetherian of dimension N, then this holds for N and every M. Okay, so we say that R is coherent if kernels and co-kernels of module homomorphisms between finitely presented modules, finitely presented R modules, are again finitely presented. So finitely, what is finitely presented? So a module is finitely generated if it is generated by finitely many elements. Finitely presented means it is generated by finitely many elements, and the relations between those elements are also finitely generated. So this means there exists an N and an M such that this is exact. But, so this is onto, and this need not be injective, right? Okay, so as I said, if R is regular Noetherian, so if R is Noetherian, then it satisfies this. Finitely presented is the same as finitely generated, and this is satisfied. And moreover, theorem that you can find, for example, in Lang's algebra book, says that if R is Noetherian, then the polynomials on any number of variables over R is again Noetherian. So this is not true of coherent, but we say that R is supercoherent if R of T1, Tn is coherent for every n, including n equals 0, meaning R is coherent, R of T1 is coherent, R of T1, T2 is coherent. Okay. So the hypothesis I need on my L is that L be regular supercoherent, which I will call RSC. So a little fact here. L regular supercoherent, then the red map is an ISO. This red map. Okay. Okay. Right. So this goes here. Right. Yeah. So theorem 1, joined with my former student Diego Montero, says that if E and F are SPI and L is regular supercoherent and Xi is an isomorphism between BFE and BFF that sends 1 to 1, then there exists a unital homotopy equivalence, by which I mean that the homomorphism is unital, the inverse is unital, and all the homotopies involved are all unital. Okay. Unital homotopy equivalence phi from LE to LF, such that K0 of phi is the identity of K0 of L tensored with phi, with Xi. So both are regular supercoherent. I mean, L is the same. And so what I'm saying is that K0 of phi goes here, K0 of LF goes here. This is an ISO, and this is the identity tensor Xi. Okay. So you can lift any such unital isomorphism between Bauer-Franz groups to a homotopy equivalence. And yeah, and then you may ask, well, so suppose that L is the complex number, right? So you have, by Rordan's theorem, you have an isomorphism, a star isomorphism between C star E and C star F. And in addition, you have this mysterious homotopy equivalence. So what is the relationship between them? And so that's theorem 2. Say E and F are SPI as before, And C of psi is a star homomorphism. Unital. Then, first of all, there exists phi from LCE to LCF unital star homomorphism such that when you complete, so you pass to the completion, I write it as a hat. It's not the Fourier transform, it's the hat, right? It's the completion. So this and the original psi are homotopic. So what does this mean? There exists an H from C star E to the continuous functions from 0, 1 to C star F, so that when you evaluate at 0 and at 1, you get phi hat and psi. So here, unlike in the purely algebraic case, in the C star algebra or topological case, what would be the elementary homotopy relation is already transitive. And this is because if you have two homotopies, you can glue them together by splitting the interval into two pieces, 0, 1/2, and 1/2, 1, right? But this is not an algebraic operation. So that's why I need a sequence there and I don't need it here. Okay. So summing up, any star algebra homomorphism C star E and C star F, maybe it doesn't come from a star homomorphism, but it comes from 1 up to homotopy. And second, the original star algebra map you started with is a homotopy equivalent. A homotopy equivalence, meaning in which sense? In the sense of C star algebras. So there is another star algebra homomorphism in the opposite direction, so that both compositions are homotopic to the identity, homotopic in this sense, right? If and only if, so C star algebraically, if and only if phi is a homotopy equivalence, purely algebraically. Okay. So, in particular, the isomorphism, the C star algebra isomorphism that Rordan tells us exists, if it is an isomorphism, it is a homotopy equivalence, right? So it is homotopic to one of these homotopy equivalences that appears here of the first field. I should warn you, there's a catch. And the catch is that when I say phi is a homotopy equivalence, I mean purely algebraically, I don't take into account the star. So the homotopy inverse of phi need not, for all I know, preserve the involution. Okay? Right. Okay, so we have those two theorems. And what about, so this is all fine and dandy with the ground is C, when the ground ring is the complex numbers. But what about if I mean, the involution on the Leavitt path algebra is defined when little l is the integers. Fix B, map E to E star, and E star to E. And if you have a ring with involution, you may ask that the involution be preserved. So you can talk about star homomorphisms between Leavitt path algebras. And then, well, you may ask whether a similar result can be proven, but where the homotopy is equivalence is a homotopy equivalence in the star category. So here you may ask, is this star algebra homomorphism? That these are star algebra homomorphism, and then you put a star. If there is a star algebra, everything is a star here, and then you put a star everywhere, right? So you may ask that. Okay. Sorry? These are, well, B of T, so the involution on T it maps T to T. So yeah, these are star homomorphism, the evaluation homomorphisms. Yeah. Yeah, and so to discuss this problem of involution preserving, so the question is whether I can prove something similar to this but preserving the involutions, right? So I need some notation for this. So R, a ring with involution. And you say you take R in A. We say that A is non-negative, which I will abuse notation and call positive, but it can be 0. If there exists n bigger or equal than 1 and x1 xn in R, so that A is the sum of xi star. So for example, suppose that R is C with complex conjugation as involution. Then A, so let's call it L, not R. So A is positive in L if and only if A is a positive real number. But we can also take L to be the same complex numbers, but with the identity as involution. So you have to accept that the identity is an involution, right? So then A is bigger or equal to 0 for every A in C. Why? Because every A in C is a square. And evolution is doing nothing, right? So this means it can be written as a sum of squares. Okay. So notice that in particular, in this setting, -1 is positive. Okay, and that I will try to convince you that where did I leave the... okay, thank you. I will try to convince you, but maybe I shouldn't say this because then you will cease paying attention, that -1 being positive is good for you. Okay, so I'm interested in this positivity of -1. And so, for example, lemma, -1 is positive if and all in LE, equipped with involution mentioned before, which restricts to little l as the involution on L, if and only if -1 is positive in little l. Okay? So this will be true with this L, and will be false with this cell. The field is the same, but the involution is different. Right. So the following example tells you that if you have a ring with involution, then you can always manufacture something Morita equivalent to it, where -1 is in fact positive. So consider n plus or minus a to be n2a, the 2x2 matrices, with the following funny involution. So you have A, B, C, D. And then the involution applied, I will not tell you what the involution applied to this is. Okay, if you are, an honest man or woman or none of the above, then this will be your idea of how to define the involution on the 2x2 matrices. Yeah, but then I put a minus here. And what effect does that have? Well, say, for example, that A is unital, because otherwise there won't be any -1 to worry about. Right, so suppose that A is unital. Then you can write the 1 in this ring is the 2x2 identity matrix, the 1. Then this is, what did I do? Yeah. Then this is, no, I should put a minus here. -1, minus. Then this is this times this. Okay, so it is positive in M2, in M plus or minus A. Okay, now notice that we have a homomorphism. The good old upper left-hand corner inclusion. And this is a star homomorphism. Because, right, if your matrix has B and C equal to 0, this is the good old involution. In particular, if it also has D equal to 0, it is the same. So, right. So, say you have two star algebra homomorphisms, then they are M plus or minus homotopic, or M plus or minus star homotopic if iota plus composed with phi is star homotopic to iota plus composed with psi. And then we have the following theorem. Let me write it here so that you can compare. Okay. Right. So Theorem 3. L is RSC with some involution. So that 1/2 is in L, so 2 is invertible in L, and -1 is positive in L. Then, if E and F are SPI, and we have some isomorphism between BFE and BFF that sends 1 to 1, then there exists phi from LE to LF and psi in the opposite direction, unital star homomorphisms, so that psi composed with phi is star m plus 2, m plus or minus star homotopic to the identity of LE, and phi composed with psi is m plus or minus star homotopic to the identity of LF. Yeah. So this is practically, yeah, and the diagram commutes so that if you do K0 phi composed with can E, you get can F composed with K0 of phi. Right, so, which is this. So we get practically the same result, but here in the stabilization, we need to, or in the homotopies, we need to stabilize by 2x2 matrices, and we need this hypothesis. Now, so what happens if we drop this hypothesis? So if -1 is not positive, we have a result which says that phi, we get a phi, but instead of going to, it doesn't go to LF, it goes to m plus or minus LF. Right? And so an psi that goes from here to here, and then you cannot compose them, but you can compose, say, you can do m plus or minus psi, and then you can compose this with phi, and well, this will give you a map from LE to m plus or minus LE. And you cannot ask that that be the identity, but you can ask that that be homotopic, not to the identity, but to I plus composed twice. And that's what happens. And the same in the opposite direction. And this homotopy, yeah, and this is a star homotopy that needs some stabilization, some further stabilization. So it's not that we don't have a result, we do, but it's not as clean as this one, right? Right. So do I have 10 minutes? So how much time do I have left, if any? Okay, yeah, 10 minutes is as I planned it. Okay, now I want to give you an idea of where this hypothesis, this horrendous hypothesis, comes from. Yeah. Okay. So the problem is that, yeah. So I mean, many times, Paul Brown. Paul Brown is a renowned person in sister algebra theory. And yeah, so I invited him for some conference that involved not only, I mean, K-theory, but not just algebraic, but also sister algebra K-theory. And he said, see, after sister algebra K-theory is like going to Hawaii. You have both periodicity, excision, homotopy invariant. But in algebraic K-theory, you have now nothing like that. So this is the kind of thing that is happening here. So say A is a unital ring. Then, well, you have seen that one can define a monoid of projective modules, or the way I want them of idempotent matrices, modulus and relation, which is the Murray von Neumann relation, and this is P equivalent to Q, means that there exists an X in P M infinity A and a Y in M infinity A Q, so that X, Y is P and Y, X is Q. No, al revés. Yeah, so yeah, this is X, Y. Yeah, no, okay. Q and P. There. Okay, now suppose, and this, and then you, this is a monoid, and then you complete it, and you, by formally adding inverses, and that's your K0. Now suppose that your ring A has involution, and you want an invariant that incorporates the involution. Then, well, you may consider the P's in M infinity A, which are idempotent, but also self-adjoint. So here the involution is the conjugate transpose, no funny signs, okay? Modulo, the star version of that, which is that there exists an X in P, so P star homotopic to Q, P and Q both projections, so idempotents which are self-adjoint. Exists a P, an X in P M infinity A Q, such that X star is P and X star X is Q. Right? Okay. And then define K0 of A star to be B of A star plus. There is a canonical forgetful map. So I forget that I had an involution. That goes from K0 of A star to K0 of A. So for example, if A is a C-star algebra, then Forge is an ISO. For example, and in particular, K0 of star of the complex numbers is the same as K0 of the complex numbers, and that's the integers. Right. For another example, well, we know this monoid, right? This abelian group, the Bauer-France group, is by definition is this quotient. And the fact that there is a canonical map to K0 simply means that those two things, if B is regular, then B and this sum are, so this is the sum of the classes, right, of the generators, are Murray von Neumann equivalent. But in fact, they are star Murray von Neumann equivalent. Because, look, I mean, by CK2 tells us that if B is regular, then B is the sum of E star, where the sum runs over all the edges whose source is B. Now, E and CK1 tells us that E star E is RE. And also that E star F is delta EF RE. Right? So these idempotents are all orthogonal. The product of any two of them is 0. And they are all Murray von Neumann equivalent to RE. Each is von Neumann equivalent to RE. So from this, you deduce that this goes to 0, not only in case 0b, not only in case 0 of LE, but also in case 0 star of LE. So we have this canonical map to case 0 of LE. Here we have the forgetful map to case 0 of LE star. And here we have a canonical map prime. This map will induce you a map from K0L star tensor BFE to K0 of LE star. And I don't know if this is an isomorphism, even when L is the complex numbers with the usual conjugation. So in which case K0 star is the integers. So this is the question. Okay, so in general, I have no idea what this K0 of L star is. Okay. Yeah, and what K0 of LE star, much less. So, and yeah, and so another bad thing about this K0 is that usual K0, the one we all love, has some nice properties, such as being, for example, satisfying excision. So if you have an exact sequence of rings, then you get an exact sequence of K0s, and which you can then complete to an exact sequence with K1s on the left. But for K0 star, we do not know whether that holds. I think it doesn't. So, so what we do? So instead, we consider K0H of A, which we define as K0 of M plus or minus star. And then we are in Hawaii. So, so for example, if L is a field and 2 is not 0 in L, then K0H of LE is K0H of L tensored with BFE. So I know how to compute it. And as a sub-example, but what about this? So if L is complex numbers with a complex conjugation, then K0H of L is C plus C, which simply says that any non-degenerate bilinear form can be diagonalized to ones and minus ones, right? So, yeah. And notice that we had a map, iota plus, that went from a ring to M plus or minus A, right? And then this will induce a map from here, so K0 of iota plus star, from here to here, which is KH, 0H. And fact, -1 positive in A implies that this map, is an ISO. And so this K0H has the good properties. It satisfies excision. It can be extended, that can be extended to the left to K, we include K1. And all these funny, on these nice properties. And if the ring satisfies that -1 is positive, then it's the same as the one we really want. Because, I mean, when, say you have a homomorphism between BFE and BFF, that tells you, you send vertices to some combination of vertices, and maybe you can, from that, you want to get a homomorphism of algebras. And so what you want to do? Well, you want to send at least the vertices, you want to send them to some projections and so on, which are really leaving projections in the usual sense. So you want this, right? But you cannot do it. You can do it. You need the ring to satisfy this, that -1 is positive, and that's why you land. In fact, you land in M plus or minus A. That's what explains, so to speak, the case when I cannot assume that -1 is positive, that my homomorphisms land in M plus or minus and not in the algebra. Okay, so I think that's my time is over, and thank you. Yeah.
In the case that the graph or the output is not
I don't understand what you. I don't hear you. I cannot discern the words that you said.
So in the case that for sister algebras, if the graph sister algebra is simple, it's either purely infinite or AF. I think there's a similar result for left path algebras.
Mm-hmm.
So about that isomorphism problem, when the algebra is simple in AF, is this?
Yeah. This is it's no problem. Yeah. You mean whether this? Yeah.
The Bowen-Franklin groups being isomorphic, does this imply?
Well, so for the case when you don't take into account the involutions, then this is in our paper with Diego. The other case, I think it's also holds, and but I mean, I don't want to say, because there might be a detail when -1 is not positive that I don't want to get into. But yeah, because essentially you are proving it for matrices. So this is no problem.
Is the definition of a homotopy in the algebraic setting you gave, has there been anything before relating this homotopy and K-theory?
Well, I mean, it's been around for a long time. Gersten studied homotopy of rings. Karubi Villamayor certainly included then. So they have this version of K-theory that is, so Quillen's K-theory is not homotopy invariant. So two polynomially homotopic maps need not induce the same homomorphism when you apply K-theory to it, unless you have some strong hypothesis on the rings. Okay. Carubi Villamayor gave a definition that their K-theory is homotopy invariant. It is also split exact. So if you have an exact sequence of rings that splits, then you apply KB for Carubi Villamayor K-theory, and then you get an exact sequence that splits, which is also not true for Quillen's K-theory. And building on Carubi Villamayor's theory, Chuck Weibel defined homotopy algebraic K-theory that is homotopy invariant and excisive and has all the nice properties, and agrees with Quillen's when the rings are regular Noetherian. Right? So, yeah. So, yeah. So this, my hypothesis that L be regular supercoherent is so that I can forget about Quillen K-theory and do and assume and do homotopy algebraic K-theory, knowing that for the nice rings I'm dealing with, it's the same. So I can use all these properties. Yeah.
Thank you.
You're welcome.